We are going to start section 4.3 today. 4.3 covers a couple topics. The first one is going to be right triangle trigonometry, which you remember from geometry. Okay, so when we think right triangle trigonometry, most of your teachers teach you to memorize the ratios using SOHCAHTOA, but as long as you memorize them, that's all that matters. So for example 1, it says the sine of phi equals 5/7. Evaluate the other trig functions of phi. I'm going to use right triangle trigonometry to do this. Okay, let's see. Sine is opposite over hypotenuse. So I'm going to sketch a picture, and I'm going to keep in mind that because this is sine, this must be the opposite, okay, and this must be the hypotenuse. Okay, so let me draw my triangle. Okay, if I make this phi, then the opposite side is 5, and the hypotenuse is 7. Okay, I want to evaluate the other trig functions of phi besides sine. Okay, let's see, I want cosine. I need to find the missing side, otherwise I can't evaluate the functions. Okay, so I'm going to use the Pythagorean theorem to get the missing leg, the adjacent side. Okay, let's call it, I'll just call it A for now. So A squared plus 5 squared equals 7 squared. Okay, now I only care about the positive root, so root 24. That simplifies because that's 4 times 6, so that's 2 root 6. Okay, so I know the adjacent side is actually 2 root 6, so I'm going to go ahead and label that side. Okay, once I have all 3 sides, it should be pretty quick to find the ratios. So I already have sine, let's get cosine. Cosine is adjacent over hypotenuse. So adjacent to the phi is 2 root 6 over 7. Okay, what else do I need? I need tangent. Let's get tangent. Okay, tangent is opposite over adjacent. So opposite over adjacent. Oh, I don't like it like that. I don't want to leave the root 6 at the bottom. So I'm going to go ahead and rationalize this. Okay, so I'm going to get 5 root 6 over 2 times 6 is 12. So the tangent of 5 is 5 root 6 over 12. And I don't see anything else I could do to simplify that. Okay, I'm going to go ahead and do the reciprocal functions then. Okay, let's see. If I do cosecant, cosecant is the reciprocal of sine. Sine is 5/7, so cosecant is 7/5. If I do secant, secant is the reciprocal of cosine, and I already found cosine. Okay, but again, I'm not going to leave it like that because I don't want the radical in the denominator. Okay, and you can rationalize it, you can rationalize it in your head after you write the original function. 2 times 6 is 12. What am I missing? I'm missing cotangent. Okay, so then cotangent is the reciprocal of tangent. Oh, actually, okay, I could reciprocal this form of tangent or this form of tangent. I'm not going to use this one because then I'll have to rationalize the denominator. I'm going to reciprocal this one, so I don't have to rationalize the denominator. So then I'll have 2 root 6 over 5, and I won't have any simplification I need to do. Okay, right triangle trigonometry is one method we use in evaluating different trig functions. The other one is using the various trig identities. Okay, some of them we already know. For example, cosecant is the reciprocal of sine. So I could rewrite that as 1 over sine theta. Secant is the reciprocal of cosine. So this is 1 over cosine theta. Okay, now tangent. What is tangent? Tangent's the y over the x, or it's the sine over the cosine. Now cotangent is the reciprocal of tangent, so I could write it as 1 over tangent, but if I write it in terms of cosine and sine, it'll be the cosine over the sine, which is why on the unit circle it's the x over the y. Okay, the other identities we often use are called the Pythagorean identities. Okay, I'm going to draw a picture. You don't need to copy the picture. I just want to show you where the Pythagorean identities come from. Let's call this theta. If that's theta, this is opposite, hypotenuse, adjacent. Okay, now according to the Pythagorean theorem, opposite squared plus adjacent squared equals hypotenuse squared. That's reasonable. Okay, I'm going to divide the whole equation by hypotenuse squared. Okay, if I do that, opposite over hypotenuse is sine, so this actually turns into sine squared theta. Adjacent over hypotenuse turns into cosine, but it's squared. And hypotenuse squared divided by hypotenuse squared turns into 1. Okay, so the Pythagorean identity, the main one, is that sine squared theta plus cosine squared theta equals 1. And it's called the Pythagorean identity because it comes from the Pythagorean theorem. Okay, there are actually two other formats of the Pythagorean identity. Okay, as long as you know the first one, you can always derive the other two. Okay, if I started with this equation right here, and imagine I divide everything in this equation by sine squared. Okay, I'm dividing everything by sine squared. Okay, so if I do sine squared divided by sine squared, I get 1. Okay, if I do cosine squared divided by sine squared, that turns into cotangent squared. Okay, if I do 1 divided by sine squared, that's the same as saying cosecant squared. Okay, this is the second Pythagorean identity. But again, if you know the first one, we can always go back and get the second one or the third one. Okay, I'm going to go back to the original function, the original Pythagorean identity. This time I am going to divide everything by cosine squared. So this by cosine squared, cosine squared, cosine squared. Okay, so if I do sine squared divided by cosine squared, sine over cosine is tangent, so that becomes tangent squared. Cosine squared divided by cosine squared is 1. And 1 divided by cosine squared is secant squared. That's the third Pythagorean identity. Again, you don't need to really memorize the second two. As long as you know the first one, you can always get the second two. I always forget the second two, but I always know the first one. Okay, for example 2, it says let phi be an acute angle. The sine of phi is 5/7. We're going to use the trig identities to find cosine and tangent. On example 1, we used right triangle trigonometry to find cosine and tangent, so I already know what the answers are going to be. This is just showing you another method that could be used to find the cosine, the tangent, or any other trig identities. It does say let phi be an acute angle. We're not going to worry about that for now, but that's saying it's in quadrant 1. We won't leave quadrant 1 until 4.4. Okay, now I am given the sine value. I want to find the cosine or the tangent. Okay, I'm going to try to find cosine next, because if I know the sine and I want the cosine, I can use the Pythagorean identity that sine squared plus cosine squared is equal to 1. Okay, but I'm going to rewrite it using the phi I want to use. So the sine squared of phi plus cosine squared of phi must be equal to 1. Because I know what the sine of phi is, it's 5/7. Okay, I could solve for cosine this method as well. 25/49. Okay, I'm going to make this 49/49 so I can subtract in my head easier. So cosine squared phi equals 49 minus 25 is 24/49. I'm going to go ahead and square root. Okay, it should be positive or negative, but we don't care about negative because we're in quadrant 1. Oh, and my angle changed. Okay, now if I simplify square root of 24, I get 2√6. Square root of 47 is 7. Okay, so this is the same answer we got on the previous example. This is just a different method of finding it. If it doesn't specify a method, you can draw a triangle or you can use the identities. Okay, I found cosine, now I need to find tangent. Okay, but because I have sine and cosine already, I'm going to use the fact that the tangent of theta is equal to sine of theta over cosine theta. Or in this case, the tangent of phi is equal to sine of phi over the cosine of phi. Okay, what is the sine? The sine is 5/7 because it was given to me. Okay, what is cosine? Cosine is 2√6/7 because I solved for it. Okay, let me get rid of those 7s. I don't want to leave the radical, so I'm going to rationalize it. So I get 5√6/12 for the tangent of phi. This is the same answer I got on the previous example. Again, it's just another method of finding it, and if it doesn't specify, it's up to you which method you would like to use. Okay, the last thing we're going to do today is we're going to simplify trig expressions using those fundamental identities that we wrote down previously. We do this to make things look nicer, to work with them easier. It's also just really fun. Okay, there's different strategies on these, but I have sine theta times cosecant theta. The strategy that you often start with is you change everything to in terms of sine and cosine, which means because the first thing is sine, I'm going to leave that alone because it already has a sine in it. Now when I get to cosecant, I want to rewrite that in another expression in terms of sine or cosine because cosecant is 1/sine. I'm going to rewrite it like that. Once I rewrite it like that, it's more obvious that the signs are going to cancel and that this expression is going to equal to 1. Now, when you simplify expressions, you do want to cancel as much as you can, but that when in the process is more important than the answer. So these you have to show your steps. These are like proofs. Eventually, you'll be proving that one thing equals another, and it's the steps that matter more than the final example, the final result. Okay, so for B, I'm going to do tangent theta times cosecant theta. And I'm going to simplify it, and I'm going to show all my steps along the way. Okay, now I'm going to rewrite things in terms of sine and cosine wherever possible. So instead of writing tangent, I'm going to rewrite this as sine theta over cosine theta. Okay, and instead of writing cosecant, I'm going to write it as 1/sine, and these are being multiplied because they're touching each other. Okay, let's see what cancels. I can cancel out the sine. And then I'm going to be left with the 1/cosine theta. And if it's possible to rewrite it without a fraction, you always try to rewrite it without a fraction. 1/cosine theta does simplify to secant of theta. Okay, secant theta is a nice simplified answer. I canceled everything I could. I got rid of all the parentheses I could, and it's a single expression at the end. Now, if I had this expression and I skipped all the way to here, then you didn't do it right because it's the steps that matter and you need to justify each step by showing everything you possibly did. Can I find them real quick? Let me see that. What do I have? Where did it go? I have that cosecant squared equals to 1 plus cotangent squared. So I'm going to replace cosecant squared with 1 plus cotangent. Okay, we're going to do a few more of these. The next one's a fraction. And there's more than one ways to do these as long as you are showing your steps. And they're all justifiable steps based on the fundamental trig identities or algebra, then you're fine. Okay, I'm going to leave the numerator alone because it's already in terms of sine and cosine. But I don't like the tangent. I'm going to rewrite that as sine over cosine. Okay, then I'm definitely not leaving this like this. Okay, how you simplify this complex fraction is up to you. Personally, I would times by cosine theta over cosine theta, but I feel like more of you have learned to multiply by the reciprocal, so I'm going to do it that way. I am actually going to show an extra step that you don't have to show. Okay, this is saying sine of theta divided by sine theta over cosine theta, which really means you're doing sine theta times the reciprocal. So this is times cosine theta over sine theta. Okay, you can skip this step if you want and skip to the timesing the reciprocal. I am okay with that. Okay, once I get to the multiplication, sine times cosine over sine, I can see that the sines are going to cancel, and I am left with the cosine of theta. Okay, I'm okay with you skipping that. You should not be skipping all the way from here down to here without showing an intermediate step. It might be sine cosine over sine equals cosine. There's different ways to do it, but you've got to show your steps along the way. Okay, we're going to do two more. Let's see, for D. D has 1 minus sine squared theta over cosine. Okay, I can see everything either has a sine or cosine, so that's not something I'm going to work with. I could split this up, but I see that big 1. Okay, I see this 1 here, and I know that according to the Pythagorean identities, 1 equals sine squared plus cosine squared. So I'm going to substitute for 1. It's going to make it bigger in order to make it smaller. Okay, so I know that 1 is equal to sine squared plus cosine squared. Okay, which looks worse, but I'm going to minus the sine squared theta over cosine. Okay, once I get here, it's obvious that the sine squareds are going to cancel. Okay, if they didn't cancel, then I wouldn't have done that substitution. I would go back and think of another plan because that one was not enough, because it wasn't working. Okay, now I have cosine squared theta over cosine. And I can cancel out one of the cosines and I end up with the cosine of theta. Okay, that's my simplified answer. Again, we could not skip all the way from here down to here because you can't cancel a cosine out of here until you cancel these first. So you have to go step by step. Okay, I'm gonna do the last one. Okay, I'm actually gonna do it 2 ways because I told you you don't need all 3 Pythagorean identities. You can always do it without. So I'm gonna do it without the other ones. Okay, it's cosecant squared x minus 1. Okay, I'm going to rewrite cosecant as 1 over sine. So this becomes 1 over sine squared x and then minus 1. And I am going to say, make sure you, when you do these squareds, make sure you put the squared here. If you put the squared out here, it means the sine of x squared and it means something totally different. Okay, I'm going to make this into a common denominator. 1 over sine squared minus sine squared over sine squared. Okay, these are equivalent because this is the same as 1 over sine squared minus sine squared over sine squared, which goes down to 1. Okay, because I see squareds everywhere, I'm thinking Pythagorean. And because I see a nice 1. Okay, where I see the 1, I'm going to change it to sine squared plus cosine squared. Okay, after I do that big substitution, I should see something cancel. If not, it was not the choice I should have made. I can see that going. Okay, I'm going to bring down what I have left. I'm not going to try to skip a step here. Okay, cosine squared x over sine squared x is a nice answer, but I don't want to leave the fraction on it whenever possible. So I'm going to rewrite this as cotangent squared x. Okay, that after I did all that work, that was not that bad. But if I had actually used the other Pythagorean identities, I could have done that a lot faster. Okay, if I go back and look at the other Pythagorean identity squared, cosecant squared, I'm going to change it to 1 plus cotangent squared. Okay, I'm going to bring down the minus 1. Okay, I can see the 1s are going to cancel, and then I'm going to be left with cotangent squared. Okay, so I got the same result when I simplified it. So even though you don't need to know the other 2 Pythagorean identities, if you see them come up and you think they might be useful, it's worth deriving them so that you can use them.